Now that we have seen what the equilibrium expression looks like and practiced with a little bit of setting up these expressions, let's do some work with solving for some unknowns. So before we do this, I just want to point out again that these equilibrium concentrations, it's not that the concentration is the same at equilibrium, it's that the ratio is the same. So you'll notice that in this example, we have several sets of initial concentrations, several sets of equilibrium concentrations, and the actual values are different in our expression, but that the ratio is the same. Okay, so it is this whole expression that is the same value and not the individual concentrations themselves. So when we are working with equilibrium constants and equilibrium reactions, it may not really be possible for us to always know all of these values, or we may not know the equilibrium constant. So we are not always just going to solve for one of these or one of these. So we want to make sure that we have a general idea of how to solve these problems. So let's think about a very simple reaction where we have A in equilibrium with reaction B. So this could be something as simple as a cis propanol going in between a trans propanol. So we have one molecule and it's slightly changing into another. Our concentration of A is 1 molar and our concentration of B is 0 molar. And this is the initial conditions. And then there's some sort of change that happens, and then we end up at equilibrium. And at equilibrium, we might know what our concentrations of our reactants and products are, and in this case, in this example, our A is equal to 0.75 molar, and our B is equal to 0.25 molar. So now what we can do is we can figure out how it changed. We lost 0.25 molar, and our change in concentration for B is we gained 0.25 molar. So you may have heard of this technique for solving equilibrium problems referred to as using an ICE table, and that stands for initial, change, and equilibrium, and what we're referring to each time is the concentration of the reactants and the concentration of the products. So let's take a look at a couple of examples. Okay, so we have a reaction mixture and we are at 780 degrees Celsius, and we have carbon monoxide and its initial concentration is at 0.5 molar. And then our hydrogen gas concentration is at 1 molar. And at equilibrium, we know that the concentration of carbon monoxide is 0.15 molar. So now, with this information, we actually have enough information to solve for the equilibrium expression. So let's go ahead and do that. The first thing we want to do is figure out what our change is in carbon monoxide. And so to do that, we take 0.5, and you could think of this as a change as we have some sort of x. So we've got some value that we're subtracting, and we see that it's 0.5 minus 0.15, so that means that it must be 0.35. So we have changed by negative 0.35 molar. That's the change in concentration. Now we look at our equation up here, and we see that for every 1 mole of carbon dioxide, we have 2 moles of hydrogen. So for our change for hydrogen must be 2 times this value. And that comes from the mole ratio, So it's 2 times negative 0.35. So that would be our change there. And then we look again at our equilibrium expression up here, and we see that for every mole of carbon dioxide, we get a mole of methanol. And so we know that we must have gained 0.35 molar of methanol. So now we can calculate our equilibrium concentrations. So 1 molar minus 0.7 molar gives us 0.3 molar. And then 0 plus 0.35 is 0.35 molar. Now all that's left to do is solve with the equilibrium expression. So we know that it's our methanols on top. And since there's no coefficient, it's just 1, right? So since we don't have anything here, the coefficient's 1, so we don't have to put anything here. You can put a 1 there if you'd like for bookkeeping purposes, but you don't need to do that. And then we have our concentration of CO2 and our concentration of H2 squared. So let's put in our numbers. 0.35 divided by 0.15 times 0.3 squared. And if we solve that, we get a K value of 26. Let's do another practice problem. So in this reaction, we've got 2 moles of methane gas reacting to form a mole of ethylene, or ethine, and 3 moles of hydrogen gas. We know that we have started off with 0.115 moles, or 0.115 molar concentration of methane, and that our equilibrium concentration for ethylene is 0.035. Here is our ice table once again. So let's fill this out. So we know that for our ethine, that we know that our initial concentrations of our products is 0. So we can put those in. And we know that our change for ethine must be plus 0.035 because that's how we get to our equilibrium concentration here. So we look at our equation up here and we see that there's 1 mole of ethine for every 2 moles of methane. So we must do 2 times 0.035 is our change, and we are losing reactant to make product, so it's a negative. And then we look at our, again, we check our equation up here, and we see that for every 1 mole of this ethylene, we get 3 moles of hydrogen gas. So plus 3 times 0.035. Now we're ready to fill out our table. So let's go ahead and do our math here. So negative 2 times 0.035 is negative 0.07. This is still plus 0.35. And positive 3 times 0.035 is 0.105. So our equilibrium concentrations here, so 0.115 minus 0.07 gives us 0.045. 0.035 times 3 gives us that 0.105, and we've added that to 0, so again, 0.105. We can build our equilibrium expression. So it's our K, and the C just stands for concentration so that you know it's not the partial pressures. So we have our C2H2 times our H2 cubed divided by CH4 squared, which is 0.035 times 0.105 cubed divided by 0.045 squared, and that equals 0.02.